So, oral final. This is the format that it will have, and the format depends on whether you are undergraduate or graduate. Because I was supposed to make some distinction, I failed to make a distinction, the workload all semester long, so it's my one and only chance to do that. Practice that I've put out there and that we'll be talking about today, that only consists of what I'm referring to informally as regular problems, something that's a bit more exploration-like, but not MATLAB. So there are 8 problems in total. So 5 of them are so if you're an undergraduate, you must complete 5 of them, or you're only required to complete 5 of them, and those will be worth 10 points each. And then on the lightning round or concept check section, there are a total of 25 questions there. So if you're undergrad, you need to complete 10 of them, there are 5 points each. If you're a graduate student, you need to do 6 out of the 8 regular problems, 8 points each, and then 13 out of the 25 concept check questions are 4 points each. So that's how it breaks down. Okay. I am willing to consider offering, like if you do excess problems, offering bonus, but I would have to do it in such a way that the maximum possible score for an undergraduate versus a graduate is the same. So I'll have to think on that. So actually anticipate somebody asking me about that. But yeah, I'm not averse to that. But I just want a situation where my grades get out of whack for one category student versus the other. Then that could become a bookkeeping issue, but we'll see. All right, so yeah, I mean, you come across certain ones like I don't know what to do this, and then you just move on. Okay. As I mentioned last time, no later than Monday evening is when it'll be posted in Canvas, and then due Thursday night, the December 7th. Oh, by the way, my other website, where the sites for all my classes, they really did take it down. Not just for me, but for all math faculty, they took the entire math department web server down.
Wait, what now?
Because we have this website, www.math.usm.edu, where several faculty, including myself, have sites. They said it was some kind of maybe security risk or something, like hacking and something like that.
Been there for like years.
Yeah,
Math.usm.edu.
it's gone. Yeah, because now if you try to go there, it'll just redirect you to the main page for the school. Now I have some.
You mean redirect you to the home page of
Yeah.
USM.edu?
Not the homepage of USM, but homepage for the School of Mathematics and Natural Sciences. And
I never go to that.
okay, well then you're not missing out on anything.
How about this website?
What?
I didn't know about the map.
Oh,
What?
Dr. Lee also has his like website.
yeah, and now it's gone too. Yeah.
Well, I knew specific professors have their own thing, like a.
Yeah.
'cause
Oh,
you-
yeah. So yeah. Well, now I think the main server didn't really have anything on it. It used to, but for I think the only purpose of the server was for faculty to have their own space.
I didn't know there was a list of like all math faculties that had their individual websites.
There used to be. Yeah.
Let me
Okay.
use it.
Yeah, so now I have this stupid little map profile on the school site where I can do my publications and that basic info, but that's nothing compared to what I used to have. So I moved it. I have it to own a domain, and I put it all over there. So on Canvas, in Canvas, Yeah, because this is the link, and this link works. So if you click on this, it will take you to the new destination. So it's not dead. It's just transported to an astral plane. And but I'd like to have a better home for it, because apparently I and other faculty will no longer be allowed to host a website of our own formatting under usm.edu. Because around here we're very PR, marketing oriented, everything has to be the same, forget academic freedom and all that. So
We're being nice to students, because that's why this college is here.
yeah.
Accessibility of knowledge.
Yeah, because okay, so all the stuff that I put for the content for this class, of course you have access to it through Canvas until the semester ends. Are you able to go back to classes you took before?
Some of them,
Yeah,
Oh.
some of them get deleted, like if the instructor deletes it.
Oh, okay, alright, but even then, I mean, I want everybody all over the world to have access to my stuff. Sometimes I get an email from somebody someplace, say, hey, I was Googling for this topic and I found your notes, these are great notes, thank you. And
On the other side of the globe.
yeah, so, anywhere.
So who's Amber C. Sumner?
She was my PhD student, some years ago, and she's currently a faculty member at, William & Carey. Well, now she's Amber Mooney. Yeah.
You and her wrote this book.
Yes, we did.
Exploration and Numerical Analysis by Dr. James B. Lambert and Amber C. Sumner.
Now we're working, and then later we put out a Python edition, and then working on one for Julia. Okay, so yeah, so that's unfortunate, but at least besides this on. Now, I digress. But yeah, so around here somewhere, like just below this, is where the final will be posted when it's ready. And I'll try to make it notify you about that. Because I can have it send a notification when this page is changed. Okay, and also same rule as for the midterm. The only questions that I will take for a final will be clarification of what the question is asking for.
What about for the review? What if you like doing the review? Or you had to ask that before the final posted?
Oh, okay, those kind of questions I'll take. I mean, questions about the actual thing.
So there's a loophole, I guess?
Well, not really, but yeah.
Kind of.
Of course, I'll take any questions about anything that is not the final. Yeah. Even if it's about the practice. So, okay. Now, speaking of that, let's get into it. One thing. So some of the problems will involve evaluating an integral numerically, using various courses like the Romberg integration or Gauss quadrant. Now, even though you're not required to do anything in MATLAB for this final, however, MATLAB can be helpful to you in checking your work. So this function in MATLAB, integral FAB, where f is a function handle for your integrand. This is approximates the integral of f of x on the interval AB. So when you work out one of these integrals using whatever numerical method on the final, you can use this to check whether your answer is at least in the ballpark. Now, the function handle f has to be what's called a vectorized function handle. That means if you plug in a vector for x, the function has to work. So for example, suppose your integrand is x squared. Then your way you define f is, okay, f sine x, and then you have to do x dot squared. It's component-wise exponentiation. Or another example, f is x e to the x. So then you have x dot star exp to x, again for component-wise multiplication of vectors. Now, some other problems with final will involve, trying to find an approximate root of a function. And you can certainly check if your value is an approximate root by using MATLAB word calculator to plug it and make sure that you're on the right track with that. So there's different things you can do to check your work before you submit. Okay. Now, I'm going to go through these, I guess, the regular problems. So what we have here is data for an Hermite interpolating polynomial. So we have 3 distinct interpolation points. So -1, 0, and 1. And at each one, you have value of f specified, and also a value of f prime. So in this example, we have 6 constraints altogether. So that means that the polynomial has to be of degree 5. So using mutual notation for every interpolation, the interpolation points are x naught, x1, x2. So n is equal to 2. So what I do is, since each point, each x value has 2 conditions attached to it, really it's like we have 6 interpolation points that occur in pairs. So I'm going to define 6 interpolation points, z0, z1, z2, z3, z4, z5, set equal to the 3 distinct x values. So z0 and z1 are both equal to -1. Z2 and z3 both equal to 0. Z4 and z5 both equal to 1. So then you can use these 6 points to obtain a divided difference table. So here we have just the index 0 through 5, and then we have the interpolation points -1, 0, and 1, but listed in pairs. And then the y values that go with them, or f of x values, is 0, 1, and 4. So this part these first 3 columns just come from the data itself. Then you have we go back here to derivative values, -1, 0, and 1. So those will get filled in here, here, and here. They go between the y values that are duplicated. Like here we have 0 and 0 corresponding to x equals -1 and -1. So here goes the derivative value. Here we have x equals 0, the corresponding f of x value. The derivative goes between them. Here we have x equal to 1, fx equal to 4, and then we have derivative value between those. All other divided differences are computed in a regular way. Like this one right here would be 1 minus 0 divided by 2 minus 1. This one we have 4 minus 1 divided by 4 minus 3, and so on. So conventional divided differences prevail the rest of the way, and you end up with this divided difference table that you can check against.
Will we use the index?
The index is not actually used.
Well, you were pointing to the index though. Or like, were you doing like Z1 and Z2? Is that what you're saying?
Oh. Okay. Hang on. I need to back up. I always do that. I should not include this column at all. Let me try that again. Wish I could edit this out the video, but it's too much of a hassle. Okay. This divided difference right here. 1 minus 0 divided by 0 minus -1 gives us 1. This one, 4 minus 1 divided by 1 minus 0 gives us 3. And so on until all the way out to, for example, this final divided difference here would be minus 4.5 minus 1.5 gives you -6 divided by 1 minus -1 would give us -3. Okay, I apologize for doing that again. I burn myself on it every time. Okay. but not hopefully confuse anyone, are there any questions about the divided difference table? And may I suggest not doing what I just did here, don't write indices as part of the divided difference table, so you don't make the same mistake that
Does
I
make
did.
it confusing.
Now, once the divided difference table is finished, then you can form the Irving-Tripoli polynomial. So you start with the coefficients along like the top row, so starting with this one, and then going down the, I guess the top diagonal, if you will. So the first coefficient in every column. So the first one is from a constant term, it would just be by itself, but in this case it's 0. Then you go to the next one where you have 1, and it's going to be multiplied by x minus minus 1, so that's the x plus 1 here. Then the next one is 0 again. That would be multiplied by x plus 1 and x plus 1 again, so in other words, x plus 1 squared. Then you go to the next one, minus 1. That's going to be multiplied by x plus 1 times x plus 1 times x minus 0. So that's why we have the x plus 1 squared times x. And then this one plus 1.5 times x plus 1, x, and x. That gives us this. And then finally, the last one, minus 3, we have x plus 1 times x plus 1 times x times x minus 1. Now remember, the polynomial as a whole is going to be of degree 5. So this is your final term here. There's no need to take the time to multiply this out and give it to me in power form. It's actually easier for me to grade when it's written like this. So see this both times. Okay. So that's the first one, is constructing an Irving-Tripoli polynomial. Any questions on it? Okay, next, Lagrange interpolation, but this is for deriving a numerical differentiation rule. Okay. Now, okay, I have a solution written down here where I use these points that are given, x naught minus h, x naught, and x naught plus 2h. And the Lagrange polynomial is based on those. However, I mentioned here a shortcut that I would strongly recommend. Look at the multiples of h in your points. So in this case, minus 1, 0, because there is no h term, and then plus 2. You can form Lagrange polynomials for these points. And then, so once you get the Lagrange polynomials for these points, you take the derivative, and then you evaluate the derivative at 0. And that'll give you the coefficients. And then you want to make sure to divide those by h in your final approximation. Here's a longer way to do it that is equivalent, where you form the Lagrange polynomials for the actual points that you're given. Notice they're not equally spaced. Just to make it a different example. So then you go through here the Lagrange polynomials, and then when you take their derivatives, in this case, you're evaluating the derivatives at x naught, and these are the coefficients that you get. Here, the h is already included in the denominator, whereas if you use a shortcut, you have to remember to divide by h in what you get. What happens is, this is the differentiation rule that you get, where the values of these coefficients are filled in. These are coefficients that are multiplying your different f values. And then when it's written as a one fraction, with 6h as the common denominator, looks like that. Keep in mind, your coefficients should always sum to 0. That's a way to do a sanity check on your answer. Now, as far as the error is concerned, how you can get the error, there's different ways of doing it, but okay. If you use Taylor expansion of your points of x naught, so x naught minus h and x naught plus 2h, and then you substitute the Taylor expansions into the approximation that you just computed. That happens over here. So here the expansions are substituted in, you simplify as much as you can, and what you end up with is, first of all of the f double prime terms cancel out. And what's left is terms that are order h squared. And that's all I'm looking for, is what is the order of accuracy of your differentiation rule. So in this case, it's order h squared. Any questions on that one? By the way, homework, I think it was homework 6, one of the section on numerical differentiation where you had to derive an error formula. That one would not have worked here. The reason is that error formula assumes that you're using all the equally spaced points in a certain range, whereas this one like skips over some points. So in this situation, it's easiest to get an error term by using Taylor expansion.
Whenever it says, what is the value of k and justify your answer?
Oh yeah.
So is the justifying your answer just
Well, I just showed you, like using a Taylor.
just how you read the like, order of accuracy?
Yeah.
Yeah, okay.
I say just by your answer because I didn't want someone just writing down a number that could be a little like a guess. Yeah, because it'd be perfectly reasonable to guess, oh, it must be second more accurate.
Mm-hmm.
Show me you know where that comes from. The book, the textbook, I don't think it's currently used, but was used at one time for modern algebra. And the beginning of every homework section would have, true and false with reasons.
Oh, there's an analysis.
Okay, next, numerical integration, Romberg integration. So here's the integral to evaluate from -1 to 1. And the idea is to get an approximation that is 6th order accurate. Okay, now, so the way this works is, when you carry out a Romberg table, fill in Romberg table with a J by J matrix, the order of accuracy of your final approximation is 2J. So in this case, since it's asking for a 6th order accurate approximation, that means that capital J will be equal to 3. So you're filling out a 3 by 3 Romberg table. And J is the number of composite trapezoidal rule approximations that you'll compute at the outset to get the to set the stage for a Richardson extrapolation. So here in this example, using composite trapezoidal rule. So here's a general composite trapezoidal rule formula, and here it's applied with here n is equal to 1, so you always start with that, and then you keep doubling n, so then n equals 2 will give us this approximation, and then you'll double n again, n equal 4 to get that. So this is the final composite trapezoidal rule approximation. Be sure to retain a lot of decimal places. Alright, like in other words, 4 minute long. Okay, so R11, R21, and R31 fill out the first column of the Romberg table. Now, once you have R11, R21, then you perform Richardson extrapolation. These are, keep in mind, this is second order accurate approximation, so is this one. When you perform Richardson extrapolation on them, you're going to get a fourth order accurate approximation. Wow, these approximations are wildly divergent. These are both pretty bad approximations. Okay, so now we filled out our first entry in the second column of the Romberg table. And this is where you use the fact that because the error in composite trapezoidal rules has this form, it includes only even powers of h, the extrapolation will cancel out the order h squared term. That's why the next approximation, this one right here, is fourth order accurate. And then, after computing R31 by composite trapezoidal rule, you do extrapolation again with R31 and R21. So from 3 trapezoidal rule approximations, composite trapezoidal rule, you'll perform 2 Richardson extrapolations to get 2 fourth order accurate approximations. And then what you'll do is form one more Richardson extrapolation from the 2 fourth order approximations. And those denominators change. So here it's 2 squared minus 1, because you're dealing with second order accurate approximations. Here it's 2 to the 4th minus 1, because these are fourth order accurate approximations in the second column. So this approximation is 6th order accurate. And then, because that's what was asked for, the Romberg table is complete. So, from the order of accuracy, half the order of accuracy, that's how many trapezoidal rule approximations you need. Start with n equals 1, keep doubling. Once you have those, then extrapolate, extrapolate, extrapolate. So,
6th order accuracy.
yeah, that's what the last approximation has.
6th order accuracy, where?
Questions about how this one goes? All right, another example. So I'm using Gaussian quadrature. In this case, n equals 3, so n is the number of nodes that you'll use. And we're integrating on the intervals 0 or 1. And we ask what is the degree of this quadruple? Well, the degree is going to be 2n minus 1. So this is going to be a quadruple of degree 5. Get that part of the question out of the way. So, because n equals 3, we need 3 nodes and 3 weights. So, first, you get the nodes and weights for the interval -1 to 1. These can be looked up like in a table of Gauss quadrature nodes and weights. So here's what they are in this case, to a certain number, like to 10 decimal places. Like this is something you can find on Wikipedia, for instance. So then what you do is we have these nodes and weights have to be mapped to the interval 0 to 1 that you're actually integrating over. Or you can do this. This is another way. This is equivalent. That so an integral over AB, a U substitution is made to go from interval -1 to 1, and So here you'd be filling in your values of A and B. In this example, A is 0 and B is 1. And then you can approximate this integral using B's nodes and weights. So there are two ways you can go about this. One is you can do shifting and scaling to map B's nodes and weights to the interval AB that you're given, or equivalently, you can use this. So how that would go in this case, so here's the original integral mapped to the interval -1 to 1 by U substitution. And now what you're going to do is you're approximating this integral by Gauss quadrature on -1 to 1. So then you have this formula for your quadrature rule, where you're going to fill in the nodes and the weights for the interval -1 to 1. What you can also do is, if you carry out the mapping, here, this is a transformation that maps your nodes for -1 to 1 to the interval AB, and then for weights, you're just multiplying it by B minus A over 2. Oh, I should go from 1 to 3, not 1 to 5. Whoops. So now we specialize in this example, A equals 0, B equals 1. So here, this is a formula that maps nodes and weights from the interval -1 to 1 to the interval 0, 1. And these are the mapped nodes and weights. So this is what you'll actually do. That your integral will be approximated by a sum from 1 to n, whatever n is, with the weights times your integrand evaluated at the nodes, and that's all worked out here. And that is your approximation. So you look up the nodes and weights, however many are needed for whatever given value of n, on the interval -1 to 1, and then you
Look up the nodes.
What?
Look up the nodes.
Yeah, well, nodes and weights. Like for example, if you go to the Wikipedia page for Gaussian quadrature, you can find nodes and weights for the interval -1 to 1 up to a certain degree. And then,
The nodes and weights at -1 to 1.
yeah, those were nodes and weights that are published for that interval. And then use these formulas right here to map the nodes and weights to the interval AB that you have to integrate over. So in this example, 0 to 1. And then you do something like this, to approximate the integral that you're given with these nodes, these weights, and these nodes for your interval AB. I recommend using MATLAB's integral function to get to the highly accurate approximation of your integral, just so you have a way of checking your Gauss quadrature result. And the same for Romberg. All right. So any questions about this one? Okay. Looks like the rest of this is all about chapter 10, root finding.
Root finding.
So for example, this first one, trying to find the root of this function using bisection. Here you're given an interval to work with, 0 to 1/2. And of course, you can usually set this equals 0 and solve for x so you know what you're supposed to get. And then make sure that your iterates are approaching that value. So your goal is to make sure that you get an answer that's accurate to within 1/16. That will indicate how many iterations you need to perform. norm. So you're gonna start with interval 0 to 1/2. So, and it's certainly gonna give you an interval where it changes sign. So in this case, f of 0 is negative, f of 1/2 is positive. So then you compute the midpoint, which is 1/4, and evaluate f at that point, and you get negative. So that tells you it's the right half of the interval, the 1/4 to 1/2, where a root must exist. Then you take the midpoint of that interval, which gives you 3/8. You evaluate f at 3/8 on your second midpoint, and you get something positive. So now you've narrowed it down to interval 1/4 and 3/8. So when you take the midpoint of that, 5/16, and the value is negative in that case. So now you have that you're in the interval 5/16 to 3/8. Now this interval is only 1/16 long. So if you choose any number in this root as an approximate solution, that would be accurate to within 1/16. Actually, what you also could have done is I could have stopped a little sooner. Like this interval right here has a width of 1/8, and therefore the midpoint of it has to be within 1/16 of the root, because this is the center of that interval, and the radius of the interval is only 1/16. And that's what I mentioned right here. 5/16 is a value that's guaranteed to be accurate to within 1/16. So whatever accuracy you want, if you perform enough iterations to get to an interval that is twice that error tolerance, then the midpoint will have the correct accuracy. That's how we can settle on 5/16. Okay, so it's a question about bisection. All right. Number finding one. Fixed point iteration. Try to solve x equals g of x, where g of x is exponential. And for the few steps here, this problem's gonna be a bit of a pain. Part A, show that there's a unique fixed point in this given interval 1 and 2. So first, you want to show existence of a fixed point. Now, a function has to be continuous, which it certainly is, because it's exponential. But you want to show that g maps the interval AB into itself. Now, by looking at the derivative, you can see that g of x is always increasing. So that's helpful, because you can see that g is going to assume the maximum at x equal 2 and a minimum at x equal 1. So if you go ahead and plug x equal 1 and x equal 2 into g, we have the minimum is 1.284 and the maximum is roughly 1.6487. Well, those values are in the interval 1 to 2, and the value of g of x at any point in between must lie within that range also. That's what you know from a function being increasing. Another way of putting it is, whatever function you're given, you find the absolute maximum and absolute minimum on the interval you're given. Then using techniques from calculus 1, you take the derivative, set it equal to 0, find the critical points, check the endpoints. In this case, all we have to do is check the endpoints, because the derivative was never 0. And if the absolute max and absolute minimum both fall within the interval that's given, then that's all you need. Okay. And that's what I'm going to do for a general function. find the absolute max, absolute min on the interval AB as you did in calculus 1. So if that checks out, then you know that a fixed point exists in the interval AB. The thing to check for uniqueness is check the derivatives. So the absolute value of the derivative must be less than or equal to some constant on AB, and that constant has to be less than 1. Now, using a similar approach with G prime, as was done here with G, the derivative is always increasing. So the derivative is found to be between this number, 0.321, and this number, 0.4122. So G prime is definitely less than or equal to some constant that is less than 1. So, so because all of these conditions are satisfied, it's continuous, it maps AB into itself, and the derivative is suitably bounded, that is enough to prove that G has a unique fixed point on this interval. Wow, that was quite a part A. Any questions about it? Dust off your Cal 1 background. Okay, and then it's a simpler part. 3 iterations of fixed point iteration. You're given an initial guess. X naught is 1.5. So to compute x1, you plug in x naught into your function g, and then you plug in x1 into g to get x2, and you plug in x2 into g to get x3, and then you're done. And if you've shown in part A that there is a unique fixed point, one thing you also know, what also gets proven, is that fixed point iteration under those circumstances will converge for any initial guess in the interval. And this does appear to be converging at least. Okay. 2 problems left. Right, Newton's method. So you're given this function to find a root of course, you can find out what the roots are. This is well, actually, that's not something you can easily do factored because it's cubic. But I do tell you what the root is. So here we're using initial guess. That's pretty close to the exact root. And let's see what happens. Because you're told what the exact root is, you can compute error also. So here we have Newton's method. So if I substitute in the function that we're given, f of x, and then this derivative down here, then we can just do a whole lot of plugging and chugging to get our areas. So the initial guess is 1.9, so we plug in 1.9 throughout here to get x1. And then you keep going. So then I plug that in here, that result x1 in here to get x2, and then plug in this value in the same formula to get x3. So now I have my 3 iterates. So now we can look at the error. So with this error we have, so here's the error the first time around, second time around, and third time around. The error is not going to 0 very rapidly. It seems like it's cut in half. So we have a linear convergence because if the ratio of errors is roughly the same, and the ratio of 1/2 is the asymptotic error constant. Now the reason why it's not converging quadratically as Newton's method normally would is the derivative is 0 at the root.
Is it degenerate roots?
Yes. Yeah. So when you have a double root, you get linear convergence with an asymptotic error constant of 1/2. So only when the derivative is non-zero at the root, do we get, the quadratic conversion set we want? So that's what we be mindful of, compute the errors and see at what rate are they going to zero. When it's quadratic, you should see the, number of correct decimal places roughly doubling from one iteration to the next. Questions about that one?
So you want us to find grade range or some order corrections?
Well, okay,
Cause it doesn't specify,
Okay,
so.
let me check the wording of the question here. Okay, really just more of a binary thing, does it appear to be quadratic or not? And if it really was quadratic, well, we can do dramatic, what?
I was looking at the wrong problem.
Oh,
Well, it doesn't ask, but.
Yeah.
Yeah, that's why.
Alright.
I'm just looking
Good
at
enough.
number 6.
Oh. Okay, something's wrong here. Okay. For an earlier version of this review, I had a comment that we prepared to do iterations of the secant method also. And I don't have a secant method on the practice. Okay. Okay, so that can happen, we're able to do secant method, but you have a formula for that. So, okay. Here we have a fixed point iteration, again, but this is not about simply applying fixed point, it's about, rate of convergence. Actually, it should not be rate, it should be order. Okay. So here we carry out Taylor expansion of involving the error. So xk plus 1 is equal to g of xk. And then x star, because it's a solution, equals g of x star. So then if you Taylor expand, okay, Taylor expansion of g, dang it, g of x k around the center x star. So that's what a Taylor expansion looks like. Now, if we look at the derivatives here, so g prime is 2x minus 2, and g prime is equal to 0 at the solution, at fixed point. G double prime is non-zero. When that happens, it's quadratic convergence. And then the asymptotic error constant, in that case, is the second derivative after root divided by 2. So in general, if all derivatives up to order r minus 1 are equal to 0 at a fixed point, and the next derivative at the root is non-zero, then the order of convergence is equal to r, and the asymptotic error constant is given by r derivative at the root divided by r factorial. So this is what the general case looks like. So in this case, r turned out all derivatives up to order 1 were equal to 0 at the fixed point. So r is equal to 2, and then the asymptotic error constant is second derivative at the root, which is 1, divided by 2 factorial, which is 2. Alrighty. Now, as for the other part of it, the final, look at your concept text, those are the kind of things that are discussed there, things that I'll be asking about. Okay. So now we're come to the end of the semester. Questions about any of this? Yes.
So, rate of convergence and order of convergence.
Are not exactly the same.
Yes.
Now, when it comes to root finding methods, like if the method converges linearly, superlinearly, quadratically, that's about order of convergence. There's a specific notion of rate of convergence that applies only in the case where the order of convergence is linear. Rate of convergence, there's a formula for that, and
Is it negative?
minus log to the base 10. Yeah,
Yes.
the number of digits you gain per iteration.
And that's, so we refer to linear order of convergence as rate of convergence?
So in other words, if the order is 1, then there is a rate of convergence. The concept doesn't make sense otherwise.
Okay, but conceptually, it's all about the speed of convergence.
Yeah, that's something we really care about. Yeah. It doesn't have to be a concept out there for some reason people do.
Yeah, why would you want to have to?
I don't know. But the thing is, not all linear convergences are created equal. Like, if you have linear convergence with a asymptotic error constant of 0.9, that's a terribly slow method. But like how I did that example of fixed point, cosine x plus 2, I really, really speeded it up. Well, in that case, the asymptotic error constant was like 1/100. So you're gaining 2 decimal digits of accuracy per iteration, which is actually, for linear convergence, it's quite nice to have that. Whereas when you have a higher order convergence like quadratic, the value of the asymptotic error constant matters less. But it has like outsized importance when it's when the order of convergence is linear. Before we close this semester down. Now, I need to review by Thursday. So, some of you have been keeping up pretty well, some not so much. However, I'm going to help you. I meant to announce this earlier.
So we have reached the end of the regular problem review.
Yes, I have. Okay. Homeworks and quizzes. Lowest 4 grades will be dropped. I have been saying 2. So just to try to take the heat off a little bit.
Wait, 4, I thought.
It was 2. I've increased it.
Very gracious.
I figure from the 15 that you need to do, that's suffering enough. Okay.
So why was 2 changed to 4?
Because
Great.
yeah. Because I imagine it can be quite stressful for several people in the class who have not turned in very many assignments. Well, actually, nobody's turned in everything. So.
Well, you have the homework to do next week, next Thursday.
Yeah, exactly. So, so I figure everybody having a lot of stress through the not just this class but their other classes.
I haven't started homework 9 or 10.
And now you have no need to.
The grading part.
Yeah. Yeah. What?
I said it is the grade that he wants in the class.
Yeah.
Anyway.
Yeah, because if you've already done homeworks 1 through 8, and then And then all it takes is having done 7 quizzes. Or if you've done excess, then the most grade gets dropped. Yeah, so this should help people. Okay, I guess that's it then.
Guys, I feel like we should clap for our last class.
Oh.
Thank you.
And this is even more so the last class, cause we're not gonna meet for the final.
Yeah.
Cause most people see each other one more time for the final, but.
Yeah, it's like,
This is sad. You say everything